We're going to talk for a second about the area of surface of revolution for parametrized curves. And I want us to recall that much earlier in our Calculus 2 semester, when we started discussing integrals, we talked about area of the surface generated by revolving a graph around the x-axis, and we had a similar formula for the y-axis. But I just wanted to pull this up and kind of refresh your memory on what that formula looked like. 2 pi times the function times the square root of 1 plus the derivative squared, and then integrated on our bounds from a to b. So this is a formula we used earlier in the semester, and this is just for a regular Cartesian function, y in terms of x. But of course, we're dealing with parametrized functions now. So we have two new formulas, which are very, very similar, right? If you look at our integrand here, it's still 2 pi times the function y, and then that's the square root. Instead of 1 plus the derivative of y with respect to x, we have the derivative of x with respect to t squared plus the derivative of y with respect to t squared. So very, very similar. And we still have it across our bounds, a to b. Notice that my a and b value here, those are going to be defined in terms of t. Okay, so this y function, this is going to be y in terms of t. So we'll just need to calculate the derivative of each of our parametric equations and then plug our y parametric equation in across our t bounds. Okay, so let's do an example. So here we have some parametric equations. X equals cosine t and y equals 1 plus sine t. And we're looking at this over the parameter t is from 0 to 2 pi. And we want to use this parametrization to find the area of the surface which is swept by revolving this circle about the x-axis. So we have these two curves, and if it was just x equals cosine t and y equals sine t, this would be a circle of radius 1 centered at the origin. But that plus 1 in my y part of the equation there, that is letting me know that these two parametric equations, what they represent, are a circle of radius 1 shifted up 1 unit. Okay, so we have a circle with a center at 0, 1. And so that's what our curve would look like if we graphed it in our xy plane, our Cartesian plane. And what we want to do here is we want to rotate this around the x-axis. So we have a formula for that. So our surface area of revolution formula is given here. S, the surface area, equals the integral from a to b, that would be t equals 0 to t equals 2 pi, of 2 pi times my y, that's what's going to go into this y value here, and then I need the derivative of x as well as the derivative of y, both with respect to t. So let's calculate those first. The derivative of x with respect to t, well, that's just the derivative of cosine, and the derivative of cosine is negative sine t. And the derivative of y with respect to t, the derivative of 1 is 0, the derivative of sine t is cosine t. So setting up my surface area of revolution formula, that's going to be the integral. My bounds are from 0 to 2 pi. And then the formula has a 2 pi in it. My y function is 1 plus the sine of t. And then I have the square root of dx dt squared, which is negative sine of t squared, plus dy dt squared, which is cosine of t squared. And of course, we write our variable of integration at the back here, dt. So we are integrating with respect to t. Everything I've plugged in now is in regard to t. My bounds are in regard to t. And I encourage you to take a second right here, pause the video, make sure you know how I've set everything up. And of course, if this was a rotation about the y-axis, we use a slightly different version of the formula. We would have plugged x in, cosine t, instead of 1 plus sine t, that part where we are in purple. All right, so now let's simplify this. So my surface area of revolution, I can pull that 2 pi out in front because it's a constant. So I've got 2 pi, 0 to 2 pi of 1 plus sine of t. Now, looking at what we have under the radical, negative sine of t squared, you're squaring a negative, that's the same as sine squared t plus cosine squared t. And of course, using our trig identities, we know that is equal to 1. So we are dealing with the square root of 1, which is just 1 here. So times 1 dt. And of course, I don't need to write that times 1, so I'm just going to erase that and take that out. So that's why that goes away. So at this point, the integration is very simple. I've got 2 pi. Integral of 1 would become t, and the integral of sine is going to become negative cosine t. And of course, we are going to be determining that value from 2 pi to 0. So I have 2 pi. When I plug 2 pi in here, I've got 2 pi minus the cosine of 2 pi. And then plugging in 0, we would have minus 0 minus the cosine of 0. So cosine at 2 pi and cosine at 0, that's the same. Those are both equal to positive 1. So I have 2 pi minus 1 minus, and I have 0 minus 1, so that's minus negative 1. We get plus 1. Plus 1 minus 1, those go away. And my solution here is 4 pi quantity squared. And so I've pulled an image in here. I just wanted you to really be able to see what we're looking at. We're looking at the surface area of this region that's created when we revolve that circle of radius 1 centered at 0, 1. When we take that and revolve that about the x-axis, we create kind of this donut with no hole. It's still donut shaped, but that hole is like basically filled in. So I hope that helps.